Good good afternoon, Internet. How are you? This is your old friend Dr. K here, rocking the mic. If this was MTV Cribs, I'd say this is where the magic happens, and I'd show you something gold plated or platinum plated or whatever. But we don't have any of that, so I'm broadcasting. Yeah, I'm broadcasting from my secret lair, an undisclosed location, which I think refers back to secret, there in the foothills of New Hampshire. So there's that. Anyway, I'm gonna see if I can get through a few slides today. Finish up chapter 6. Right, that seems to be going on forever, but let's just see if we can finish it up. We're just winding it down. We only have one more concept to talk about in this chapter before we sort of go on to the next thing. This is actually, believe it or not, a sort of a preview of the stuff that's coming up. The next chapter is a lot more on eliminations and so forth and so on, and a lot more into the nitty-gritty of those kinds of things. But anyway, let's just start with this. I think we ended up somewhere around this slide here. I'm using by the way, I'm using a tablet. Oh, how high-tech of me. I'm using anyway. So I think we actually talked about this slide already. All right, this is HMP Oompa Dee Doo. I've got I don't like the look of it. I'm sorry. See, you didn't even know there would be a musical portion of this. This is like a variety show. Let's just say that. Anyway. So I'm just gonna continue. I'm not gonna stop. I'm gonna stop singing. I think we've already talked about this. This is no reaction because vinylic positions and benzylic phenyl positions and vinyl positions are not reactive to our SN2 type of reactions and stuff. So I think we talked about that already. Let us go on to, where are we here? We are at, all right, the elimination reactions of alkyl halides. And again, we started this last time we were chatting, and let's just continue on here. So we talked about SN2 a whole bunch already, all right? So we know how, if we have some sort of a substrate that is unhindered, right? We can attack the back side of that carbon that has a leaving group on it, and this being a decent nucleophile, which is fairly small, has a negative charge associated with it, which is localized. We can have the straightforward substitution of a bromide here for a methoxy species. Okay, but when you have that SN2, you have not just this presence of a great nucleophile in this methoxide thing, right? But you also have, of course, the ability of this methoxide to also act like a base, right? And so whenever you have a situation where you have a strong nucleophile, you also have a strong base presence, right? Because when we talk about substitution, we're just talking about something like a base acting like a nucleophile. It's the same exact species, but just a different employment of it. We're just calling it something different because that one reaction is going to be different. All right, so that's what we're really sort of talking about. All right, and so what we have here is instead of a substitution reaction here, we have an elimination reaction. Why can we have an elimination reaction? Because we have protons here which are in the beta position, right? The beta position, right, to this carbon. This carbon here is the alpha position. This is a beta carbon. This has beta protons on it. If you have beta protons here, and you have things that are, in one sense, might be talked about as a strong nucleophile, those same things could be talked about as a strong base. So this guy here, instead of acting like a nucleophile here, will act like a base. It'll just pull off that proton right there. That will swing on down to establish a pi bond, and that will kick that off, right? And this will give you your double bond right there. And again, we've sort of already talked about this. We just began with this last week, but let's continue on with it so we can talk about something else that's very similar to it. Okay. So when we have again, so choosing the appropriate base / nucleophile is important, because you want to, since we know that SN2 and E2 reactions are in competition with each other, we have to choose the correct reagent to favor the thing that we want. All right, so this is our sort of what do you call it? our intention for it, for what we want, right? So here we have this propyl iodide, we have terbutoxide and terbutanol, right? And we have a 15% SN2 reaction where this terbutoxide here will act, right, like a straightforward, tablet, right? And we'll hit the backside of that carbon there, kicking off that iodine right there, giving us our tert-butyl propyl ether, right? And 15%, not very good yield, right? It's not, of course, it's not a very good yield because this is not a very good nucleophile. Why is that? It is just a very big species. Ideally, nucleophiles want to have, want to be a smaller species that are, again, very strong, that is, have a very localized negative charge if possible. This guy here has a localized negative charge, but it's just a very big thing, all right? So instead of acting like a nucleophile, Bubba here wants to act more like a base, right? This guy here wants to act more base-like, wherein instead of attacking the backside of that carbon, maybe it wants to go for these beta protons. Now, I keep on talking about beta protons, of course, because we have to have them in order to have an E2 reaction, or any elimination reaction for that matter, right? But here you have an 85% of an E2 reaction, right? This again, this brand new. Let's say this is the brand new bond that's formed. That brand new bond that's formed is formed from the abstraction of that proton right there, and that pair of electrons right there swinging on down to form that new double bond, which will be right up, which will be right there. Okay, so this guy here is going to be the brand new bond that is formed from this guy right there. Okay, after this kicks off. So there's that. All right, and so when we talk about E2 reactions, we talk about, well, many things, right? But the one thing that we can talk about is that if we have a halide as a leaving group, that specific reaction, right? That specific reaction is called a dehydrohalogenation. That means you are removing a hydrogen here, right, and removing a halogen in the same, pretty much in the same step almost, right? And it doesn't have to be in the same step, doesn't have to be sort of concerted, but this is what we call an E2 of a beta hydrogen here that also kicks off a halide, right? So here is your dehydro. You're pulling off that hydrogen right there on your beta carbon here, and you are losing this guy right there. So there's your dehydrohalogenation. It's an E2 reaction that has a halide as a leaving group, essentially, all right? And that's what it looks like completely, all right? Notice something else here. Notice the temperature here. Eliminations, all of them, including the E1, are favored if you add a little bit of heat to it. Right? So if you have a little bit of heat to it, the reaction happens a lot better. All right, a lot more efficiently. All right, so if you are concerned that your reaction is going to compete heavily with SN2 or SN1 for your E2 and E1 reactions that you'd like to do, throw in some heat. It's going to help your elimination status there. Okay, so that's going to help you out a bit. All right. All right. So what other things? Pardon me. So what things can we talk about in terms of, like, how do we run an E2 reaction? All right. Well, one of the things that we do, if you can see from here, we're using, in these cases here, we're using terbutoxide, right? Right, and we've talked about what terbutoxide, how I like to talk about terbutoxide. I say if we use potassium terbutoxide, which is a very popular E2 base, it's a big bulky base, right? And terbutanol. Notice the similarity. Sorry, but it's crooked, my stupid tablet. All right. God, what is going? Okay, everything's falling apart. What is going? All right. All right. If I'm using this potassium terbutoxide, I made this potassium terbutoxide from taking terbutanol here and removing that proton there, right? That proton there with, let's just say, potassium hydride. That hydride will pull off that proton right there. That will bubble off as H2 gas. H2 gas, right? Let's just write it out. How's that? Huh? Is a positive charge? Is a negative charge? And this is not, well, I mean, this is not necessarily an ionic species. I'm drawing it out for you so you can see where the negative charges are coming from, though, right? All right. All right. This hydride here is going to grab that proton right there. That pair of electrons here will swing on back towards that oxygen, and the H2 will bubble off. Plus, you will have our aforementioned potassium terbutoxide. Now, when we used potassium terbutoxide and terbutanol, I like to, just in the first shorthand way, call it toke and toe, right? Why is that? Because it looks like a T here. It's not an OK and TOH. So toke and toe is my sort of shorthand way, because I use it a lot for talking about potassium terbutoxide and terbutanol. All right, but how do you make that? Normally, you make potassium terbutoxide or sodium terbutoxide or any of the alkoxide bases by taking your favorite alcohol, right? Not your favorite alcohol, but let's just say like a synthetically useful favorite alcohol. Although your favorite alcohol for synthesis might be ethanol. Knowing you, who knows how much of it you have just lying around willy-nilly. All right, who know? I'm not judging. I'm not judging you. Come back. I'm not judging you. I'm just chatting here, right? I'm sitting here in a corset and heels, just chatting like friends normally do over the internet. All right, that's all we're doing. Nothing personal there, right? All right, so we take your alcohol here. Let's just say it's ethanol. Let's just say it's ethanol. What the hell? We'll just say it's ethanol. And if you take sodium metal, which is sodium to the 0 oxidation state there, you form sodium metal H2 gas, which bubbles off, which is really good for Le Chatelier's principles because we get to remove some of our byproduct, which drags the reaction rightwards, right? Making our alkoxide, in this case here, if I'm using ethanol here, it would be the ethoxide plus sodium, so hence sodium ethoxide plus H2 gas. Or if we just use NaH, we can just say that we make that hydride just directly because we have the hydride there and the sodium there directly, and that hydride pulls off that proton right there. All right, so that's how you make your alkoxide bases. All right, and so whatever you do, when we do E2 reactions, the best thing you should possibly do is this: take your base that you want to make. Like, let's just say if you want to make ethanol, if you want to make ethoxide, make your ethoxide, or you can just use your ethoxide, right? Write that down here, but the solvent that you use should mirror that. So if it's sodium ethoxide, you should run it in ethanol. If it's, I don't know, isopropoxide, which is totally fine too. If it's potassium wow, that's off. I can't, this pad is crazy. Hold on. If it's isopropoxide, lithium isopropoxide. What the hell? Right? We'll switch up our ions a little bit. If it's a lithium isopropoxide, use it in isopropyl alcohol, common rubbing alcohol. All right. So there's that. So just make sure that you use the analogous alcohol with your alkoxide base. It's going to help you out, and there's lots of great reasons for it. We talked about that very early on, actually, but we'll talk about it again in discussion. So when we come into discussion, let's just chat about that. All right. So again, there's that. E2 reactions. The E2 reaction is just like what we talk about for an SN2. An E2 reaction just depends on the concentration of your substrate and the concentration of your base multiplied by some fudge factor, which will give you the rate of the reaction. So E2 refers to the fact that it's a bimolecular, just like an SN2, except the rate of it depends on, just like SN2, the concentration of your substrate and the concentration of your base and some factor there. Okay, so just like SN2 that way. Okay, mechanism for an E2 reaction we sort of already talked about, but here's it drawn out in nice sort of cartoonish detail here without my graffiti. Although I will graffiti it. I'll put a guy who's dead. A dead guy. I'll put a dead guy there. How's that? All right. So take your ethoxide here, pull off your beta proton. There's that. Here's your verbiage there. A new pi bond, which I've already talked about here, is formed right after this guy here gets abstracted. And this guy here gets to form here. And this ethoxide here is involved in this transition state, wherein you have a transition state here, of course, but there's no intermediate. An intermediate, it would be more or less isolatable or isolable here. But for E2s and SN2s, there's no intermediates. There's only transition state. So here is the transition state, which denotes motion or movement. So your ethoxide is pulling off this proton, which is in the process of leaving that carbon, which is in the process of forming that double bond, which has this carbon here, which is in the process of having this bromide here leave. All in one felled swoop, all right? Partial bonds in the transition state, all right? So now at the very end you have your fully formed alkene here with your ethanol here. Your ethanol, of course, comes from this guy here, and your bromide here comes from the leaving bromide over there. Okay, make sure that you don't just pay attention to this, my meanderings on the internets here. Make sure you go on. You have to play with this yourself. Do dozens and dozens and dozens of E2 reactions, and then also E1 reactions as well. All right, and here's your E2 reaction. Just as we have promised, there's only one transition state. Which, if you want to look at the transition state, it is this one over here. That's how it's mostly going to be, right? Second order overall bimolecular reaction. Now, the E1 reaction is again really similar to an SN1 reaction. It's a unimolecular reaction. And the E1 and the SN1 share a common transition state. I'm sorry, a common intermediate, right? The first thing that we make here is this carbocation. We have a very weak-ish type of base / nucleophile here in water or alcohol or something like that. The rate determining step here is the ionization, which we talked about, from this chloride here, in this case here, to your carbocation. This guy here leaves, and this is the rate determining step or the slow step. Now, if you have water here as a nucleophile, this will give you here your tert-butanol product here, right, as your SN1 product, all right, as your nucleophile. But if you have a little bit of heat or a little bit of or some other reasons why water would act as a base, you will also get some of the E1 reaction, right? And the E1 reaction is dissimilar from the E2 only in the fact that it's not a considered process. Like the leaving group doesn't leave while the proton's being abstracted. So in E1, you have a stepwise mechanism versus a concerted mechanism like the E2. So the E1 is not concerted, the E2 is concerted. All right, here's a mechanism for an E2, and we'll go over this very quickly because the next few slides there's some better data there. Okay, so in this case here you have this. I don't know why this publisher wrote this stereochemistry, weird stereochemistry here, but anyway, tert-butyl chloride. Here's your rate determining. Well, let me take a drink of, let's call it water, but who knows what it could be. It's clear. I can tell you that. That's good. Well, hold on one second. This is great. Wow, water. Let me just. Okay. Oh, okay. It's good. I'm gargling with water, not with, for example, absinthe. For example, just in absinthe, I'm just pulling out of the thin air. Right? If you could only pull absinthe out of the thin air, right? Anyway, that's a joke. Never mind. Don't have to laugh at that. Anyway, so here's your tert-butyl chloride here. The rate determining step is the ionization of the species here. The chloride leaves. It's a slow step here. Here's your carbocation. Now here you have a fast step here in which either the water acts either as a base here, right? In this case here, it's acting like a base because we're talking about the E1 reaction, but it could also act like a nucleophile. But here we're talking about the E1. So here we have water here that will pull off this proton here. Notice this proton here, right? Don't get confused. This proton here is a beta proton. You have beta protons here, here, and here. All right. This just so happens to be. Let's just say it's this one. I think it probably looks that one. All right. Let's just say this is this one. Right. It's off of that carbon. You have beta protons here, but you also have 3 here, 3 here, and 3 here. All right. So that's where that is. All right. So this water here pulls off that beta proton here, giving you your E1 product, right? And your H3O plus as a byproduct, okay, which is only going to help you later on down the line when you have to help this guy here ionize more tert-butyl chloride. All right, so this is the E1 product here, right? All right, that's what we talked about. But another competing mechanism, of course, right, is also going to be the SN1 product, the SN1 mechanism, wherein the water doesn't pull off the beta proton here, it just jumps into that carbocation, fulfilling that carbocation's need to not be positive anymore, right? It'll just jump right in there, giving you your new oxygen carbon bond right there, and then having water again pull off that proton there, because this has to stay, because it's, you have to neutralize this positive charge. And notice the final products on both the SN1 and the E1 are neutral, just like the starting material. So if you begin with this with a neutral starting material, you have to end off with a neutral product, more or less. All right. Now your intermediates, right, can be all kinds of charged if you want them to be, right, or if that's what the reaction calls for. But not, you can't have your final product be charged. Okay. So you have, so here you have your water here pulling off that proton there, again, equalizing that off. Now I want you to notice one more thing, which we talked about the E1 product and the S1 product being a neutral species. Notice what's happening here though. This water here is pulling off a beta proton, and it is quenching essentially that positive charge. It is removing that positive charge. It doesn't, this guy here is acidic because this guy here wants to quench this positive charge, right? This water can't normally pull off an sp3 hybridized carbon, sp3 hybridized proton. That's insane, right? That doesn't happen. But this proton here is more acidic because it's next to a carbocation, right? This guy here has a polarized carbon-hydrogen bond here, which is very, very, very weak now because it's next to a carbocation, right? So that's why this water can pull off an sp3 hybridized carbon more or less, all right? But notice what's happening here. This guy here is pulling off this proton to quench this positive charge here. The same thing that is happening where the water here docks into that carbocation, again, still removing the positive charge there. It does not, even though this is a stabilized stable carbocation, more or less, it's a tertiary position, right? Still doesn't want to be positive. It'd like to be neutral. It'd like to be more, again, ultimately towards that noble, status, right? So this is one way to remove that positive charge. Here's another way to remove that positive charge, either doing an E2 to quench it here, or doing an an E1 to quench it, or an SN1, right, to dock into that carbon to remove its positive charge. All right, so that's just some details about it. Okay, but here's again the energy diagram for an E1 reaction, which we did before for an SN1 SN2 reaction to show you sort of how things go. All right, so your first step here is just the halving of the starting material here, and from here to here, this guy here is the activation energy, right? The large E, right? Activation energy. From here to here, this is the thing that begins the reaction. From here to here is the activation energy. This is delta G of activation. All right. Will give you your first transition state, right? Your first transition state here, from here to here, is the ultimate leaving, the in process leaving of the chloride here to give you your intermediate carbocation here, right? This is your transition state. Here's your intermediate. All right. So transition to here to your intermediate. Now you have the fact that you have now this carbocation, which is a stabilized thing, right? Now you have this. Right, and now you want to go to the next thing. All right, so let's just see if we have the next slide that tells you a little more about this. All right, so here's your transition state, which is the leaving of this, which shows the leaving of the chloride, and then now you have your carbocation. So that's what this shows right here, aided by a polar solvent. Right, in this case here, you have a great polar solvent, water or methanol or whatever, something that's going to help it, but you have some solvent that has to be a polar species to help support the existence of this carbocation. All right. In this case here, the carbocation that's formed is sort of your ideal case. It's like this tertiary carbocation, right? And this tertiary carbocation is sort of stabilized by the fact that you have lots of polarity in this oxygen here. This oxygen here has lots of partial negatives. Here's a full positive for you. This water here will sort of surround this carbocation, giving you a stabilized overall species. And plus we talked about that funny thing, hyperconjugation, as the reason why this tertiary carbocation is so stable. Now we will get into a whole lot more of carbocation stuff and rearrangements next chapter. This is where it really takes off, but this is sort of your intro to it. This is sort of the calm before the storm. All right, so now you have this carbocation right there. Okay. Okay, so now where we left our heroes, and they are now right here. Now going from here, and now you encounter another transition state. Now this transition state here is now not where like the chlorine comes back in or the water comes back in an SN1. In the case here, you have a case where you have, I'm going to draw this, if I can draw it really crudely here. Here's you have your carbocation that is now being slowly quenched, or being quenched in some respect, by the existence or by the appearance. I'm going to draw dots. Dot, 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 dot. That's grabbing that proton over here. And this guy here is now weakening this bond here. Dot, dot. I should have dotted this line here altogether. You know what? I'm going to dot it again. I'm going to go back. I'm going to dot it again. All right, here's this. All right. I'm going to draw just one. Draw this here. Here's your hydrogen over there. Here's your H2O over here. Okay. Here's your carbocation. I'm going to draw the carbocation fully here, though. Okay. So dot 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 dot. I'm going to grab that proton over here, which is going to make this guy here, this carbon hydrogen bond over here, very weak. So dot 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 dot. Pff, wow. Good show. I can't. I can't deal with this tablet. Okay. Dot dot. Okay. So this H2O, this crazy looking, drunk looking H2O, is grabbing that proton over here, right, which is beta to this carbocation, right, which is then now weakening this carbon hydrogen bond over here, which is then now enhancing the existence of this pi, this incoming pi bond right there, right. This is again in transition, all right. This shows motion, and then after this is done, then it cascades all the way down here to give you your final product, which is your isobutylene, which is this guy right here, which I'm sure is drawn in a much more coherent fashion in the next slide, and presto. Yes, it is. All right, so this guy here pulls off this proton here, which is made more acidic, right, due to the adjacent carbocation, right? Again, this guy here is, if you look at it just like this looks like an sp3 hybridized carbon. This is this is like pKa 50 normally. If there's a proton here, it'd be like pKa 50, and this water would be like, hey, what's up? You're like, yeah, whatever, I'm out, later for you. I'm like, I know you're out of my class, but I know, but whatever. So they wouldn't be talking to each other. Now, though, this thing here, so now this guy here has a positive carbocation. This guy has a carbocation. Now it's all like, hey, I'm all right, I'm available. You're like, yeah, all right, whatever. And so then it grabs the proton, right? And then because now this is more susceptible to leaving, because now this carbon bond wants to form this pi bond even more so, hence weakening this bond over here. This guy here, you can imagine, is being more and more polarized towards that carbocation, hence weakening that end of the covalent bond. All right, so there's that. All right, how determined whether the substitution or elimination is favored? This is the European spelling of favored. Let me write it out for you guys who are from Boston. Favored. All right, so how to determine whether the substitution elimination is favored or favored? If you're from, I don't know, Canada, I have no idea. I don't know. Anyway, so all nucleophiles are potential bases, and all bases are potential nucleophiles. All right, substitutions. So that's something that we talked about for a long time. All right, substitution reactions are always in competition with eliminations. We talked about that. Right, and there are different factors that can affect which reaction is favored. Okay. So how do we determine what is what? Well, first we have to make sure that we know what's in competition. The first thing that's in competition is SN2 versus E2. An SN2 reaction will be the direct attack of some species that has a negative charge, ideally, on a unhindered carbon species, unhindered carbon with a good leaving group on it, right? So the A route here is, this goes from here, hits the backside of that carbon over there, but bang, kicks off the leaving group right over there, and there you have your brand new carbon nucleophile bond here in your SN2 mechanism. Okay, but now if you also have beta protons, you can always have competition no matter how great your SN2. I guarantee you that you will have a little bit of E2 always on the side if you don't properly frame your reaction. And we will go into how to properly frame and sort of soup up your reaction for either SN2 versus E2, depending on what you want. But if you have a beta proton, you can bet all of your bippy that you're going to pull up some of that beta, right, to give you some of that pi and to give you this alkene species. So SN2, E2, always in competition. Rarely are they not in competition, only if you really stack the deck in the favor or favor, as they say in Canada, of one. Why am I picking on Canada? What did they ever do? Well, they give, oh yeah, Bieber. They gave us Bieber. That's why I'm picking on Canada. All right, so there you go. You found the reason why I'm bitter. Although I like Alanis Morissette and Peter Jennings, they're from Canada. But Bieber, yeah, that's it's inexcusable. Take back Bieber forever, and I'll stop making fun of Favord. Okay, there's that. All right, so where was it? Before I get on my rant. Oh yeah, E2 and SN2 competition. Blah blah blah. All right. Okay, with a strong base, that favors E2. This is weird though, right? This is a weird way to talk about it, right? With a strong base like ethoxide here, you favor SN2. Look at the way that this is what the publisher suggests I use as a slide. It says with a strong base, it favors SN2. This is wrong verbiage, right? I think they must mean with a strong nucleophile, because here, if you have mostly an SN2 reaction, 90 to 10 anyway, of SN2 versus E2, ethoxide here is acting more like a nucleophile, not like a base. So this guy here is ethoxide acting as a base. This guy here, no, right, acting like a nucleophile, a nucleophile, right? And this guy here is acting like a base. All right, so this is not a good way to talk about an SN2 reaction as a base, but as a nucleophile. Here you have some where it's acting like a base, but mostly it's acting like a nucleophile. All right, and how do you and so what's favored more or less? Well, if you have an unhindered substrate, it's going to act more like a nucleophile. But as soon as you start tacking on some steric hindrance to it, it's going to be more E2 like. So this is, again, I keep on talking about why organic is hard. It's not hard because there's a ton of stuff to memorize, which you shouldn't be memorizing anyway. It's you using your own instinct as to being able to determine what kind of a substrate is more appropriate for SN2 versus E2 versus E1 versus SN1. You know, it's sort of the balancing of all that knowledge between, you know, reagents and appropriate use of substrate. All right. So with a strong base E2, it will favor E2. Now this is something I agree with, right? Using the base to favor E2, sure, absolutely. Why? Because this guy here is now not a primary substrate. This is a secondary substrate, right? This is a secondary substrate. Has lots of, and I'll draw these in for you here. If we're looking at this thing as a nucleophile, this guy here has gobs and gobs and gobs of steric hindrance, right? So if you use ethoxide here as a nucleophile, it's like, I'm gonna go in the back door, right, ba-boom, and I can't, because I can't really get back there very well, because I have all the bulkiness from this H2 over here and these 3 H's over here. I can't get behind there. I can't do it. All right, so fine, consolation prize. Screw you. I will take. You know what? I'm gonna take one of those. How's that? I'm gonna take a Twinkie and then leave. I'm going to say, fine, I'm going to grab that proton, to hell with you, I don't need your stupid SN2, I will be fine being an E2 reaction right there. And I'm going to grab those protons. If I grab protons, oh, I don't know, A, I'll have isomer A, for example, right? But if I grab protons B, and I'll redraw it down here, if I draw a bit, come on, bromine. It's like a halide for good buddies, like a bromine. Hey, bromine, what's up? All right, there's that, there's this, there's that. All right, take your ethoxide, grab those guys right there. That zips over there, kicks that off. Let's just say those are protons B. And you'll get, oh, they don't even have it here. They don't even have it here. Oh, my word. Shame for shame, Wiley. All right, so these guys here are both A. right? Both A, right? For shame, Wiley. You have another isomer that they don't write down for some reason. I have no idea why. But if you pull off that proton here, then you will get, like we talked about before, this other one, like this other thing here. Here you have the internal alkenes, and there you have the terminal alkenes. And these two guys here were got from the fact that you can choose either that proton or that proton in your Newman projection. So at home, you should. Who know? Are you home? Are you home right now? I have no idea. If you're home or not home, draw the Newman projection of this guy here, and you'll see that if you fix this in space just once, right? If you just draw your Newman projection, like willy-nilly, there's no stereochemistry here at all. It's not told to you, so you can just be doing whatever you want to do. There's your bromine over there. There's your hydrogen over here. There's your methyl over there, and then you'll have two hydrogens. There's one over there. You'll have hydrogen over there, and then you'll have a methyl over here. Now, if I pull off this proton over here, it will, and this is anti to this bromine over here. This will give me the trans product. All right, but imagine if I were to turn this Newman projection around, just a back carbon anyway, and have the methyl go on that side, and then have that proton be down here, and pull off that proton there at that point, then I would have the cis. Right? Make sure you can do that for yourself. Make sure, right? Your book talks about it. We'll talk about it, of course, in discussion a whole bunch. But make sure you can, and I think we even ended off on that, I think, last time we had class, all right? But you can have two diastereomeric alkenes here, plus one other alkene, which is not necessarily a diastereomer of it, right? It's a sort of more of a constitutional sort of isomer, sort of it, all right? And then again, because no matter what, this is still hindered. This is a secondary position. It's hindered, no matter what it is. So when you have a hindered substrate with a good leaving bond here, you're always going to favor elimination, as evidenced by that ratio of 80-20, right? But you can still have you can eke out a little bit of SN2 if you want to, possibly, right? By giving you a little bit of that species over there, all right? So that will give you a little bit of SN2 here, backside attack of the ethoxide on there too, not very good, but you can still do it, all right? So there's that. Tertiary substrate never, oh, look at that. Now, here's something for you. I love how they do this. Okay. Look at this. This is actually a great slide. I love this slide, all right? And it would be really good if I looked at these slides sometimes a little bit beforehand. Today I didn't. I was like, I'll go it cold. I can do this. Anyway, look at this. E2, highly favored when you have a strong base and a hindered substrate. Look at this. Crazy great. This ethoxide, in this case here, can pull off, any one of these three protons, or these three protons, or these three protons, and to give you your E2 product. Okay, highly favored, very stable. You'll realize why it's stable next chapter. Okay, so you have your E2 and 91%, pretty good ratio. But look at this, you have a competition for an SN1 for the ethyl tert butyl ether. Wait a minute, I thought we talked about the fact that E2 could only compete with SN2. So SN2 and E2 were the only competing things. Well, this is the most popular thing that is the competition. But that's not in every case. In science, there's no always or never, except if you say there's always going to be exceptions. Then you can always use always, right? How's that for like deep philosophical shit, right? You'll always have exceptions to your always or never rules, right? Except in the case where you'll never have anyway, I'm not a philosopher anyway. So E2. So there's your E2 right there, which is obvious, right? You have 9 protons that you can pull off in a dehydrohalogenation process, right? Very simple, very straightforward. This pulls off that proton over there, that kicks down like so, giving you your isobutylene, right? Here now you have an SN1. Where's the SN1 come from? Well, it sure as hell doesn't come from the fact does not do an SN. This is SN1, not SN2. There's no backside attack. This must leave in some ionization process to give you a very small amount. Very, very, small amount. Eliminate that last L. I can't erase. I don't know how. Small amount. Very small amount of that carbocation. All right. And when you have that small amount of carbocation, then I guess some ethanol can come in and jump in there. But man, oh man, this is not favored at all. I mean, I'm even you know what? I never knew this value. And I'll check into this. I'm not convinced completely that 9%, that a 10 to 1 almost of SN1 to E2 actually exists. But this is what Wiley says, and I'll believe him, but I'm not convinced just yet. But anyway, you can have this because if you have a tertiary substrate and you have a polar solvent, you can have some of it. It can theoretically happen. It's not likely and definitely not favored. So in the case here, you will definitely have the E2 as your major product, okay? But again, there's always going to be some exceptions. Just when I ask you the test question, I'll say, well, what's the major product? And you'll tell me that this is the major product. You'll never tell me this is the major product. If I say a minor product, there might even be other minor products that are better than the SN1 the SN1 competing product. All right. So here's where it gets a little bit, I mean, here's like a slide that just tells you some nice summary. Bases are nucleophiles where they're small versus bulky. Okay, same substrate, butyl bromide, N-butyl bromide. So the N, the normal butyl bromide, the one bromo position. We have sodium methoxide and methanol, a very strong but very small nucleophile or base. However you want to talk about it, base or nucleophile. Right? In the case here, it's small, so it's going to favor SN2, right? Favor SN2 because why wouldn't it? Why the hell? It's easier. This guy here is going to attack the backside of that guy. Oopsie, sorry. Come on, stupid. Come on. I'm not type A, but even I get a little bit. Come on. Backside of stupid tablet. All right. Gives you that guy right there. Gives you this guy right there. All right. Your E2, of course, comes from the beta elimination. Right. The beta elimination of those protons right here. All right. But if you all of a sudden make, and again, we talked about this before a few slides ago, or pretty much every slide coming up to this one almost. Right. If you have a bulky nucleophile or base, it's gonna be a lot more energy to attack the backside of this carbon over here because you'll have a lot of hindrances from this carbon chain here. So it's more likely, it's easier that this big bulky base will just pull off. This bulky base here will just pull off a beta proton right there. Incidentally, bulky base was my nickname in college. All right, so right there. So there's that. And that will give you the major product of E2. All right, so there's that. Here's something. Here's this is a weird slide. I will admit to this directly. It's a weird slide, but it's worth talking about, I guess. You have a weak base here. Why is it a weak base? Because it would be a strong base if you didn't have this additional carbonyl here. It's a weak base, so because this guy here, a weak base or a weak nucleophile, because this guy here is a delocalized oxygen, right? You have this resonance here. Draw a resonance arrow. I'm going to draw the other resonance contributor species over here. All right, so you have this acetate ion here, which is in resonance with this other acetate ion canonical form as well. All right, this is pretty weak. All right, but so you won't have this won't have the impetus to either directly attack the backside of this guy here or pull off a proton here on the beta position in a very quick way. It's a very weak base or a very weak nucleophile. So why will you have more SN2 and no more SN2 and no E2 at all? Well, it's a weak base. It won't have the energy to pull off these beta protons here. It's more likely to act like a nucleophile because if you have acetate or acetic acid in here, it is actually going to act more like a polar solvent than a strong nucleophile. So you'll have some ionization of the bromide right there. Some partial ionization here. I know it says SN2, but SN2, it's weird to think about SN2 and SN1 as opposite ends of a continuum. You always think of SN2 and SN1 as the ends of a continuum. Like you have, it's more SN2 like than SN1 like, more SN1 like than SN2 like. Here, if it's saying SN2, it's saying directly that this oxygen here attacks the backside of that carbon over here, kicking that off, which if it says it does more or less. It has more SN2 character, but I would argue the fact that it would not be a complete SN2 process. I would, if this is a stereocenter over there, I would bet you that there'd be a little bit of racemization, because you'd have a little bit of some ionization process there. All right. So there's that. I think that's a decent, that's a decent explanation. This is not completely an SN2, but it's more SN2 than anything else. And there's no E2 because, again, these protons here are pretty dang strong. Pretty hard to pull off for an acetate ion. You look at your pKa for your acetate. You'll see that it's not compatible with that. But now you have a different story. Now you have ethoxide here, which is similar in terms of carbon count than acetate, but you have no carbonyl, and then you have a very strong base here. Here you will have a direct E2 here, which is much more obvious to see. It will pull off those protons over here, swing it on down here to give you your double bond, your new pi bond here, and kick off your bromide. All right, so that will happen right there, right? And you'll have some SN2 competition, just not a whole hell of a lot, because you have some hindrances there. You have a secondary position here, not a very good SN2 substrate, because it's hard to get in between, between those bulkinesses of those two methyl groups here, just like we talked about before. All right. But the point of this slide, you have a base here, which is a strong base here, because it is not polarized, and you have an identical carbon counted base here, which has polarization here. It has some resonance here, and it gives you more SN2 here. So the take-home message here: if you have a base that is polarizable, chances are you'll have an SN2 competing process here. That'll give you an SN2 product. But if you have a non-polarized base here, you'll have more of an E2. All right. Now it's going to be your instinct to memorize that. Please don't do that. Please do problems. Problems will help you out here. Do more problems and check answers, and then that will calibrate your thinking. Studying from this slide here is good for theory, but not good for remembering the entire thing, where you have to do your problems. Okay. All right, tertiary halides, SN1 versus E1 and E2. All right. Ethoxide, strong base, we talked about this before. There's almost no chance of having an SN1. Almost no chance. But this is not a zero chance. You know that you have some. If this is ethanol, if this is ethanol here, if this is ethoxide here in ethanol, you can have some SN1. Why? Because I just told you, because we just found this out a few slides ago. So these are not, this is a publisher's typo at this point. Okay. So here you can have it's just going to be the overwhelming majority of this guy here being the E2, the dehydrohalogenation process, is the overwhelming preponderance of an E2, right? Because you have a strong base pulling off a proton there, kicking that off, kicking that down into kicking the bromide off here to give you your E1 right there, right? But your SN1 over there, is going to be very, very low, okay? If you have an ethanol here with heat, you have a polar solvent here. So here you will have the bromide here leaving to give you a carbocation here, which will give you some E1 process and some E2, I guess, but not a whole lot. It'll be more E1. But if you have a carbocation, it'll be a lot easier that this ethanol here will dock into this carbocation. All right, it'll be a lot easier for that. Okay, so here you'll have some You'll have some ethanol here that will dock in here, giving you your final, ethyl terbutyl ether. And you'll have some here that you will have some process here that will give you some of the E1 process. So your E1 process here will be in competition with your SN1 process here. But heat will favor more elimination, right? But why does it give you some SN1 versus E1? We'll talk a lot more about that as we go into this process more so. Okay, so there's that. All right, so make sure that you'll see that if you have a strong base, you're going to favor if you have a strong base, you will favor more of the and you have a tertiary substrate, you'll favor more of the E2. If you have a weak base here, you'll favor more of the E1 SN1, the E1 SN1 process. All right, so that's how that works out. Here's your overall summary. Please have this, but just don't study this. Study real problems. Don't study this. All right, this is not going to work out really well for you. All right, it's a general slide. All right, always just work with problems. Okay. Okay, so here's where I give you some answers here to some problems here, but work on them for yourself. Okay, so take this 1,4-terbutyl bromocyclohexane here and sodium cyanide here, and run the mechanism where you will see that this will invert the stereochemistry. Please make sure you can draw this out in a chair conformation and see if this makes sense. Can you run this reaction here? You actually get this product here, but please don't just follow the mechanism that is given here, but draw out the actual chair and what should be where, and see if we can actually do this reaction comfortably. See if it works out. Where is this terbutyl going to go? Where is this bromide going to go with respect to the terbutyl in its best case scenario? Here you have a case here where you have an intermolecular SN2. Again, a very straightforward reaction, although it doesn't look like it is. You have a hydride here pulling off this proton here, and when you have that, then you have formed your alkoxide, your alkoxide base, which is in the same molecule as your leaving group. So it's an intramolecular SN2 reaction as opposed to an intermolecular. This is the same exact reaction as if you were to take, propyl iodide and you treated it with, I don't know what, ethoxide. Ethoxide is the same exact process here, except the ethoxide here is a different molecule than the propyl iodide. This guy here will attack the backside of that iodide right there, giving you your 1, 2, 3, right? For oxygen here, 4, 5. 1, 2, 3, 4, 5. Here is an intermolecular, I-N-T-E-R, molecular. Intermolecular, if you can read, intermolecular, right? SN2 versus intramolecular SN2. It's the same exact thing. Please draw out this mechanism and make sure it makes sense to you. Here's some SN1 reactions here. Now SN1 with racemization, right? So you have your even though this is not a stereocenter here, it forms an sp2 hybridized carbocation, which has no stereochemistry associated with it. This did it, even though it's not R&S stereochemistry. It is, it is cis-trans. It is cis-trans stereochemistry. All right. So please make sure that this mechanism makes sense to you. So you protonate this guy here with HCl. Then this guy here leaves, forms this carbocation right there. Then the chlorine here from your HCl can either attack from the top face here, or can attack from the underneath side of this carbocation, giving you the other one. Make sure this makes sense to you. It's a racemized process. Make sure that you can do this, right, and make chairs out of these to tell me which what kind of stereochemistry is associated with this isomer here versus this isomer here. The chlorine attacks from the top face versus the bottom face. So what I would do here, I would even draw a chair of this. Even though it'll look weird drawing a chair of a carbocation, let me get you started, right? Here's your terbutyl position right here. This guy here, instead of drawing it axial versus equatorial, just draw it like a straight on out there, right? And you have a, there's that. That's not even, look at this. So look at that. Draw it where you have the chlorine is attacking from the top face of the ring here versus the bottom face of the ring, and show me what it ends up looking like in terms of your bond line notation and your chair conformations. Tell me what that looks like at the very end, okay? All right, so this is a sort of an Easter egg, all right? So I have a problem here which is not on your original slides, but what I'd like you to do, I'd like you to do out this reaction mechanism for me, okay? This is an E2 reaction. It's an E2 reaction, okay? And this E2 reaction, now you've known from the previous slides and even our previous lectures that E2 reactions only happen when you have beta protons, right? And how many sets of beta protons you have there determine how many alkene products you can have, you know, as per our last slide. This guy here has beta protons. This guy here, which is your leaving group here, has beta protons all around it, right? All around it. But you only get one alkene product. You only get one alkene product. So why is that? What I'd like you to do is please write your answer on the inside of a folded piece of paper. So take a piece of paper and fold it right down. It's an 8.5 by 10 paper or whatever, or 8.5 by 11. Fold it in the middle. Write your answer, right, and then fold it so it looks now like half of that. All right. And before you fold it, put your name. Put your name, legibly written name, so I can read it, please. Okay. Fold it up. Right, fold it on a folded piece of paper with your name on it and put it on the stage before the beginning of class on Wednesday, the 12th of November. So that's this Wednesday, right? I'm giving you some points for it, but it's an all or nothing point of view here, right? And you will not be getting them back, right? I'm going to take them, see that you did it right, give you some points associated with it, or not, and I'm going to throw your paper away, and I'm not giving it back to you, period. All right, no late submissions, no like, I was late to class and I couldn't, whatever, so can I give it to you now? No. No late submissions, you know about it now, okay? So November 12th, which is a Wednesday, all or nothing, okay? So do that. Again, this is an E2 reaction, but you only get one product, even though you should get two. Tell me why, but then draw, Dre, I'm Dr. Dre. Right? Draw your answer, draw the mechanism as to why. So why? So draw the mechanism as to why. As to why that is the case. Okay? Alright, folks. Thanks for having me chat at you and talk at you and from the interwebs. Sorry I had to be out today, but things were beyond my control. Okay, have a good rest of the goddamn whatever the hell it is. All right, peace out, yo, and all of that. All right, later on, folks. Bye-bye.